Hello, my name is Nick Livolsi, and I worked alongside with Dr. Gideon Simpson. Um, and our research was a parameter study on a spring mass system. I'm not going to go a lot into the backstory. I'm also not going to go a lot into this code because it's a lot. So if you have any questions for me about it, I'm pretty sure I'll be available today. These are all presented, so please ask them away because I know when I did this at first, I had a lot of questions. So anyway, so our kind of purpose of this was to test out different sample sizes and variances to find out which is the best combo, when generating synthetic data. So we wanted this data when we generate it to be like if you were in a lab doing it, like you were pulling on a spring with a mass, you were finding the forces, stuff like that. So yeah, and we used that data and we integrated using Newmark's method, but instead of using like just using it as if like you take the certain displacement, multiply it by the Springs constant, we use the exact forces that we generated, and we compare that to the exact solution, and we try to figure out which combo of variances and sample sizes has the least error. So first function I did, I kind of explained it. It's just generating the synthetic data. So it is kind of it represents like data that would be generated in lab in person. As you can see, it has like some noise to it. So yeah. Next function, I call it a lookup function. If you look at the commented out set function, that was our original lookup function. It didn't work out though because ended up not working because as if say we're integrating this from t equals 0 seconds to t equals 1,000 seconds, we notice that the position, there's a time graph in that it would grow, like the oscillation would grow, which means which is like represents the position of the the displacement of the mass would be increasing, which means that the energy in the system will be increasing, which doesn't make sense. So we use interpolations instead, which is basically like it takes the exact data that we just generated and it gives it a certain displacement, and it basically says this would be if we calculate that certain displacement, this would be the exact force of it. So that's what we return. These next two functions are intertwined. So I'll talk about them as one. This one first. This is the Newmarks. As I said, the Newmarks method is what we're using to integrate this because it's specifically designed to integrate spring mass systems. So the thing with Newmarks method, if you go down here, you'll see it has a beta and gamma variable. In order for Newmarks to work, beta needs to be in between 0 and 1/2, while gamma needs to be in between 0 and 1. As long as they're in between there, Newmarks will work. So this for loop is integrating it, and that what's really going on in this for loop is this function. So this is Newmark's method. Newmark's method is a system of nonlinear equations. So it takes a lot so you have to solve it nonlinearly, which is why we use a NL-solve package. NL stands for nonlinear. And what it does is it finds the zero of the function, kind of finds the zeros of the system. So and those zeros end up being the new position, velocity, and acceleration is what we calculate. And if you notice in here, this third equation, this is where we are replacing the k, which is spring constant, times the position with the exact force. This is where the exact force is added, and this is where the exact force replaces the force that would just be calculated from data. And lastly, we go to our last function, which is actually calculates the error. Again, these are all just setting the variables. This right here, exact Tmax, is, since spring mass system is just a second order ordinary differential equation, we can actually solve it for the exact solution. So this is the exact solution, and we replace the t for the max Tmax, so it's the last the solution at the maximum time. We did 1,000 trials of this, and as I said, actually I don't know if I mentioned this, but these were our different variance and sample size combos that were used. For variance, we had 0.01, 0.1, and 1, and sample size we had 10, 100, and 1,000. And this random seed is in there so we can replicate this experiment, which is really important. Then this calculates the error. So for each variance, And that for loop is for each sample size. So it does it 9. So it does it 3 times here, then over. So it ends up doing it 9 total combos. Excuse me. It calculates the approximate position. So I call it approx, just XAPX for short. And it takes the last calls the newmark function, which returns the last position, which is the position of our integration at Tmax. So it takes that, then it calculates the error, which is that minus the absolute value of all that squared. And then it divides that afterwards. It divides it by the trials, which in this case was 1,000, and it pushes it into array. And so it does that for all the different combinations. And then lastly, that would end up being a 9x1 array, but I wanted to make it look nice, so I reshaped it to make it like a 3x3 matrix. So the columns were the variances, different variances, while the rows were the different sample sizes. That is it. So if you have any questions, please ask them. I know this is a lot. This is a lot of code. So if you have them, please ask them. Thank you so much for watching this video, looking at my research.